your question answered?
Yes.
Okay. All right, so I got a box sliding up a ramp that's initially going at 30 meters per second. Assume the ramp is tall enough or long enough so that the box is not going to fall off the edge. The question is, how far up the ramp will the box slide? And will the box slide back down? We're gonna, so this combines what we did in chapters 2 and 3 and with what is happening here in chapters 4 and 5. All right, so the two problems we're dealing with, it's a linear motion problem, constant acceleration, and the other one is that it is a force problem. So from the how far up, so the distance aspect of it, we take our quantities of x, the initial, the final acceleration, and time. We know two things. What are the two things that we know in this problem? Say it again?
Initial velocity?
Yep. And what is the initial velocity?
30 meters per second.
Kevin has just set our coordinate system right then and there. When he said 30, not negative 30, he is establishing that to be the positive direction. All right, we know one other thing.
Well, the acceleration
What's the acceleration?
would be 0.
No, if the acceleration is 0, that box is never stopping.
Is the final velocity 0 because the stopping are?
Yeah. That's the other piece of information. Now we need three things in order to figure out the other two, but we don't, given in the problem, we don't have that, but we do have enough information to find the acceleration. So that brings in the chapter 4 and 5 stuff. So now we're going to go through our facades process. Force diagram of box on ramp. We've done it many times. And there's friction. So which way is friction acting on it? Coordinate axes. Now, the coordinate system that we're going to pick should match. Well, there's two ways of going about this. If we go with what Kevin started with, then up the ramp is positive. You also could make, nope, we skipped the acceleration phase. In which direction will this box, what will be the direction of acceleration for the box? Why?
Because the box is going to slow down as it goes up.
Yeah, if it's slowing down, acceleration is the opposite direction. So we have established now, acceleration is in this direction. So we can pick the coordinate system that Kevin started with, which is the initial positives in the same direction as the initial velocity. Or we could make the acceleration the positive and flip it around. Personally, I like it in the direction of the initial velocity there. It is anti-parallel to the acceleration, but as long as it's not perpendicular to the acceleration, we're probably good, or some other angle. So if we establish then up the ramp and perpendicular to the ramp. So what am I breaking up? Now that we're at the decomposition phase.
Wait.
And so it now becomes, see, y is going this way, friction is going this way. I also have W cosine of theta. And, oop, that's a lie. W sine of theta and W cosine of theta. Since I don't have any forces going up the ramp, how is it moving up the ramp?
From the initial velocity.
In essence, because I said it was going up the ramp. I don't need a force to justify why it's going in a particular direction. Some particles come into existence already moving. It doesn't have to start anywhere. Equations of motion. How many equations of motion will we have?
2.
And whose voice have I not heard today? Kelly, I haven't heard your voice today. Give me one of the equations of motion.
I'll be honest, I'm very lost right now,
Ah,
so let's back up.
why don't you tag to someone else? Pick someone to give me the equations of motion. Do you want me to pick for you? Say for Kira, I haven't heard your voice today. The worst that happens is you're wrong. Just take a chance.
Would one be tension?
I don't have tension in the equation.
Well,
This is why this is normal force, if that's the one you were thinking of. This is weight times the cosine of the angle, friction, and weight times the sine of the angle.
okay, yeah, normal force minus weight cosine
Like you mean it.
cosine theta equals 0.
Done.
Okay.
Boom. All right, we have another one. Doris? Want to take a shot at the next one?
Normal force.
No, she's already done the normal force one. We've got the J hat equation right there. We're looking for the I hat equation, the one that's going in this direction, that's going parallel to the ramp. Brewer, or Kelly?
Weight sine theta equals
All of these equations, we do equations of motion. The left-hand side is always going to be the forces to start out with, and the right-hand side is going to be mass times acceleration for that direction. So this is equal to 0 because there's no acceleration in that direction.
W minus friction, so W sine theta minus friction equals,
Mass times acceleration.
Say it again?
Mass times acceleration.
All right,
V negative, W sine
yeah. So, I assume you were gonna chime in, you.
Yeah, I was gonna say, since friction and they're both going in the same direction, that makes sense to, I was gonna say that.
Okay,
But I was gonna say sine theta minus friction equals MA, I wasn't gonna say anything, so that makes sense.
so you were gonna leave that off?
Yeah, but that makes sense.
But, yeah, I have two forces in the negative direction because of the way that we defined the positive direction. We got two negative forces here. All right, so what kind of friction is this anyway?
static.
Did somebody say dynamic?
I said dynamic.
Okay.
But
Generally called kinetic, but dynamic, people will know what you're talking about. So we have this kinetic friction, only one object, so I don't need the subscripts for the other things. And there we go, we got our two equations. Substitution time. For what do we have an independent equation?
weight,
And,
friction.
yep, those are the two. That one. What is the formula for weight?
Mass times G.
Okay. And you could just shorten it, there's nothing wrong with what we just said. mg also works. Which is a source of irritation. I looked at some of the text readers, the automated computer text readers. Whenever they came to this equation, they would say W equals milligrams. No. All right, and the formula for kinetic friction?
U sub K times what?
And what's the symbol that goes in between?
Equals, oh, yeah, should it be equals?
Yeah. It's the static one that's kind of iffy. Kinetic one is equals. All right, so that's what we're gonna plug in there. So from the first equation, I'm gonna also go ahead and bring W cosine theta over. Is equal to mg cosine theta. And the other one, I have negative mg sine theta minus mu sub ky equals ma. We've done the substitution. It's now time for solving. Well, I'm gonna take this, plug it in for y. It's convenient, we had that nice simple equation there. So y, no. Negative mg sine theta minus uk mg cosine theta equals ma. Now, right off the bat, what am I expecting my acceleration to be?
Zero, one.
Negative.
All right, so negative, and also it should be, the magnitude of it should be less than 9.8 meters per second squared. So somewhere between 0 and negative 9.8 meters per second squared. And again, I'm expecting negative acceleration because, well, we define positive the opposite direction of acceleration. Mathematically, how would I solve for A?
Divided by M.
Okay, if we divide by M, cancels out over here, and I'm left with A equals, well, conveniently, they both have M's in them, so that M and that M cancel out with that M. I'm left with negative G sine theta minus mu k G cosine theta. Now it's plug and chug time. Negative 9.8 times the sine of 40 degrees minus 0.4 times 9.8 times the cosine of 40 degrees. gonna change one thing I said earlier. It is gonna be negative, just as Louise said, but it's not necessarily gonna be in between 0 and negative 9.8. I can have acceleration greater than the acceleration due to gravity. Yeah, I just got carried away. So other people got the same answer? All right. So I now know the acceleration. I can pop it into here, negative 9.3 meters per second squared. And so now I can figure out the displacement. What equation should I use to figure out to get the displacement? Since I know VI, VF, and A.
V final equals velocity initial plus acceleration times. Yeah.
Did you change your mind halfway through that, or
Oh, yeah. Yeah, yeah. No, I didn't change it.
you did not change your mind? We don't know time. We could use it to find time if we wanted to. There's a one-shot equation if we want to find the displacement.
Final velocity squared minus initial velocity squared plus 2 times acceleration times the displacement.
All right, I'm going to correct one thing. Notice that in that equation, the VI and the VF do not have vector symbols over them, or they shouldn't. It's this. That's the final speed squared equals initial speed squared, and then the other two are vectors. Because it gets, since there's two ways of multiplying, when you talk about a vector being squared, typically you're talking about dot products, but there's also cross multiplication, so I think, well, I flip back and forth whether it's acceptable or not, but technically it is speed. So final speed squared equals the initial speed squared plus 2a dot delta s x, whatever, I guess I'm using x there. And again, Nathan has suggested using a different equation. We could have used that to solve for time, and once we had time, we then had two other equations we could have used. So 0 equals 30 squared plus 2 times negative 9.3 times my displacement. Negative 900 divided by negative 18.6. Just shy of 5 meters, 4.9 meters. Say it again.
48.39.
4839. And you had the decimal point here?
Yeah, after 48.
Oh, okay. I had a decimal point off of my head. All right, so the thing is going to slide up 48.39 meters. And then it's going to stop. But will it slide back down? So as soon as it stops, what changes in our force diagram?
Initial velocity.
Oh, okay. Changes in the force diagram.
Oh, sorry.
It would be the start of a new problem where the initial speed is 0.
Friction,
What about it?
it would go the opposite direction.
Yeah. So friction is acting down the ramp until it stops. As soon as it stops, friction flips directions. So our force diagram now, I have weight acting down, I have friction acting up the ramp, I have normal force acting that way. So we're sort of reworking the problem. So it'll look very similar to what the equations that we just had, those equations there, except, well, it stopped. It's sort of a brand new problem here. If it accelerates, which way is it going to accelerate now? I've seen thumbs pointing in two different directions. It looks like I see 3 thumbs down the ramp and 1 thumb up the ramp.
Down the ramp.
Down the ramp, okay. So my acceleration will indeed be down the ramp. So let's set up a coordinate system as such. I'm gonna make that I hat and J hat. I could have kept the same convention as over there, but why? And so we've got, oh, so decomposition. Weight gets broken up yet again. W sine theta down the ramp, W cosine theta into the ramp. Friction up the ramp and normal force perpendicular to it. Since we're trying to figure out whether this thing is going to be sliding down the ramp, we first need to check, or in essence, what we're checking here is, does it overcome the static friction? So our equations of motion, we'll have 2. All right. Kelly, did you want to go for it?
Can try it.
Yes.
Normal plus friction.
Perpendicular, you want the ones that are sort of in line.
Oh, weird. Minus weight times cosine theta. Equals, would be MA, right? And negative A,
Which way is it going to accelerate?
down.
Yes, and Y and W cosine theta, are those up or down the ramp?
Oh, so it equals 0.
Yes.